For as long as human beings have looked up at the night sky, we have projected our deepest fears and wildest myths onto the red dot of Mars. We are conditioned to see it as an older, tragically dying world, either a static, dead rock or the home of some lost, highly advanced civilization. This hand-drawn network of intersecting lines catalyzed the myth. In the late 19th century, astronomer Giovanni Schiaparelli observed canali, meaning natural grooves. But when translated into English, a profound error occurred. They were recorded as canals. An affluent American astronomer named Percival Lowell built an entire observatory specifically to study these supposed structures. Lowell became convinced that these lines were the desperate engineering projects of a dying alien race, working collaboratively to pipe water from polar ice caps down to their parched equatorial cities. Modern robotic emissaries have since proven that Lowell's canals were merely an optical illusion. The real story of Mars is a frozen planetary crime scene, uncovering a history more violent and spectacular than anything early science fiction writers imagined. Travel back 4.6 billion years, and Mars would be unrecognizable. In its infancy, it was a fraternal twin to Earth, a warm, blue world. Beneath the surface, it possessed a churning, molten core of liquid metal that operated as a colossal internal dynamo, generating a powerful planetary magnetic field. This magnetic field acted as an immense deflector shield against the young sun's ferocious solar wind. Safe beneath this protection, Mars accumulated a heavy, dense atmosphere rich in greenhouse gases. This thick atmospheric blanket trapped the sun's heat, keeping the planet stable and warm. With high atmospheric pressure and warmth, Mars held an abundance of liquid water. Torrential rainstorms carved intricate valleys into the southern highlands, while in the north, these river networks emptied into Oceanus Borealis, a colossal ocean covering nearly a third of the Martian globe. But right at the beginning of its life, Mars was subjected to a cosmic robbery. According to the Grand Tack hypothesis, the giant planet Jupiter migrated inward toward the Sun like a massive gravitational wrecking ball. As it swept through the inner solar system, its gravity devoured the vast majority of the raw planetary building materials. Mars was starved, left as a planetary embryo with only 11% of Earth's mass. While early Mars was a stable paradise with the exact prebiotic recipes required for life, this stunted physical mass was a ticking time bomb locked inside the planet's architecture. The death of this world is dictated by the laws of planetary thermodynamics, specifically the square-cube law. Because Mars is so much smaller than Earth, it cannot hold on to its internal thermal energy. Imagine a small cup of hot coffee set out in the winter air. It will lose its heat and freeze solid, while a giant vat of water stays warm for hours. Mars was that small cup of coffee. Over a few 100 million years, the internal magma oceans began to cool. The swirling convection currents inside the molten iron core slowed, grew sluggish, and eventually ground to a halt. Around 3.7 billion years ago, the Martian geodynamo suffered cardiac arrest. With the death of the core, the mighty magnetic shield completely vanished. The invisible force field that had protected the planet for 1 billion years was gone. Mars was left entirely naked and exposed to the brutal environment of space. What followed was a planetary execution. Without a magnetosphere, the charged solar wind slammed directly into the upper atmosphere. In a process called sputtering, these high-energy particles literally knocked atmospheric molecules out of Mars's gravitational grip, stripping the skies away ton by ton. As the atmosphere thinned, the barometric pressure plummeted. This caused the boiling point of water to drop, until the rivers and the vast northern ocean began to violently boil away into vapor, even at low temperatures. This water vapor rose into the unprotected sky, where ultraviolet sunlight blasted the molecules apart. The light hydrogen escaped into space, while the heavier oxygen sank back to the surface. It encountered a crust rich in iron and triggered a planet-wide chemical reaction. The oxygen bound with the rocks to form iron oxide. Mars literally rusted. Revealing tone. Recent analyses of modern escape rates has challenged the assumption that Mars lost all its water to space. Mathematical data indicates that between 30 and 99% of that ancient water was actually absorbed by the planet itself. Through crustal hydration, the water molecules were chemically locked into the crystal structures of the planetary crust and buried subterranean glaciers. The death of the interior has left Mars with a stagnant lid geology. Unlike Earth, which has shifting tectonic plates, the Martian crust is one solid, unbroken shell. On Mars, a rising plume of magma stays in the exact same location for billions of years, pumping lava onto the same spot over and over again. This topographic view captures the result: Olympus Mons. It towers nearly 14 miles high, 2.5 times Mount Everest. Its base covers an area the size of France, with an incline so gentle its summit remains hidden beyond the planet's curvature. Where the crust swelled to create these volcanic titans, it tore open elsewhere. This is Valles Marineris, a tectonic scar over 2,500 miles long. If placed on Earth, it would stretch uninterrupted from New York to Los Angeles, plunging 4 miles deep. These monolithic structures are the frozen, extreme scars of a world whose internal engine permanently failed. Step onto the surface today, and you would find an atmosphere at 0.6% of Earth's pressure. This is below the Armstrong limit, where the boiling point of water drops below normal human body temperature. Without a pressurized suit, the liquid in your lungs and blood would instantly begin to bubble and boil inside you. This whisper-thin air cannot retain heat. During the polar winters, temperatures drop so low that 30% of the global carbon dioxide atmosphere literally freezes out of the sky, falling to the surface as dry ice snow. In the spring, sunlight passes through the ice and warms the dark sand underneath. This traps pressurized gas until the ice violently cracks. Dry ice geysers blast dark basaltic dust hundreds of feet into the air, creating the sprawling dark patterns known as Martian spiders. As the air warms, localized heating creates immense dust storms. These storms are crackling electrical generators. The dry dust grains rub together to create massive amounts of static electricity. This powers gargantuan dust devils, swirling tornadoes up to 12 miles high that act as invisible, crackling lightning towers. We have even been able to listen to the soundscape of this world. Because the atmosphere is composed of cold, dense carbon dioxide gas, the speed of sound on Mars is 30% slower than on Earth. Bizarrely, sound on Mars travels at 2 different speeds. High-pitched sounds travel through the gas slightly faster than low-pitched sounds. If someone were speaking to you from a distance, the high notes would reach your ears before the low notes, fragmenting the audio into a distorted acoustic experience that science is only just beginning to comprehend. For over 6 decades, humanity has been relentlessly flinging its greatest technological marvels across millions of miles of deep space to solve the riddles of this complex world. But exploring Mars is a brutally unforgiving endeavor. Aerospace engineers even share a dark, ongoing joke about the Great Galactic Ghoul, an imaginary cosmic monster that feeds on spacecraft traveling to the Red Planet. The statistics warrant the humor. More than half of all robotic probes launched toward Mars have met catastrophic ends, burning up in the atmosphere or slamming at terminal velocity into the basaltic regolith. Before we sent machines to the surface, human observations were filtered through the lens of romantic imagination. Astronomers like Percival Lowell popularized the idea of a neighboring sister world, sketching intricate maps of what they believed were lush, fertile canals built by a dying, highly advanced civilization. In 1965, NASA's Mariner 4 probe successfully beamed back the very first close-up digital photographs of the Martian surface, delivering a profound shock to the human psyche. Instead of Lowell's canals, the black-and-white images revealed a dead, heavily cratered, hyper-arid moonscape. But Mars was simply hiding its true anatomy. In 1971, Mariner 9 arrived and was greeted by a ferocious, completely opaque global dust storm. As the dust slowly settled over the coming weeks, orbiting scientists watched in astonishment. Gargantuan volcanic peaks, the massive expanse of Valles Marineris, and the winding scars of ancient dry riverbeds finally emerged from the shroud. These discoveries proved that Mars was a dynamic, complex geological system. The presence of these features suggested that the planet had a violent, active history, raising the possibility that its past could have supported more than just geology. In 1976, NASA launched the historic Viking missions, the most ambitious biological expedition in human history. They landed two sophisticated, nuclear-powered robotic laboratories, Viking 1 and Viking 2, directly onto the Martian surface. These machines were equipped with highly sensitive miniature laboratories designed to scoop up the soil and hunt for the active metabolic signatures of living microbes. The initial results were incredibly dramatic. In one primary test, Martian soil was mixed with a specialized radioactive liquid nutrient broth. Instantly, the mixture began to erupt with radioactive carbon dioxide gas. To the scientists watching, it looked exactly as if millions of unseen microscopic Martian organisms were consuming the food and exhaling gas. However, a second instrument designed to detect the baseline organic molecules that make up all known living things returned a completely flat reading. It detected 0 organic molecules in the soil, not even the basic carbon compounds found in lifeless meteorites. This reaction wasn't biological, it was chemical. The dirt was rich in highly reactive chemical salts called perchlorates. When these salts were exposed to the warm liquid nutrient broth inside the Viking ovens, they initiated a fierce reaction that aggressively destroyed the organic molecules while releasing carbon dioxide gas. The Viking landers had literally burned the exact chemical evidence they were searching for. We mistook fiercely hostile Martian chemistry for Martian life, demonstrating just how deceptive the planet's surface could be. Following the Viking missions, NASA shifted to a mobile, geological approach. In 1997, the Mars Pathfinder mission arrived, utilizing a revolutionary landing system that enclosed the spacecraft in a massive cocoon of bouncing airbags. It successfully delivered Sojourner, a microwave-sized rover, to physically traverse the ancient floodplains of Valles. This mobile strategy was scaled up with the twin rovers Spirit and Opportunity. Right at its landing site, Opportunity discovered millions of tiny, near-perfectly spherical hematite pebbles blanketing the soil. Mission scientists nicknamed them Blueberries. These concretions only form in the long-term saturated presence of mineral-rich liquid water, proving that the plains of Meridiania Planum were once a shallow sea. To find out if those ancient waters contain the chemistry required to support living ecosystems, NASA built a nuclear-powered rover the size of an SUV, Curiosity. Because it was too massive for bouncing airbags, engineers invented the Sky Crane, a rocket-powered descent stage that hovered and gently lowered the 1-ton rover onto the surface on nylon tethers. Curiosity landed inside Gale Crater, a 3-billion-year-old impact basin. Using its robotic rotary drill, Curiosity bored into ancient, petrified mudstones and successfully extracted highly preserved complex organic molecules, including thiophenes and benzene, shielded from damaging cosmic radiation inside the mud. These robotic pioneers proved that Mars once possessed the exact chemical building blocks and freshwater environments necessary to sustain microbial life. The hunt for biology continues with the mystery of the Martian methane plumes. Robotic rovers and orbital sniffers have detected localized spikes of methane gas rising out of the bedrock. Because methane is destroyed by ultraviolet sunlight within a few hundred years, its presence means something must be actively producing it right now. There are two primary explanations. On the left, a geological process called serpentinization occurs when hot water reacts with volcanic rock, releasing methane. On the right is a biological hypothesis. Dormant colonies of extreme microbes that wake up during the Martian spring, metabolize nutrients, and exhale gas that filters up through the crust. While we search for life beneath the crust, the panspermia hypothesis suggests that Martian life might have already visited Earth. Large asteroid impacts can blast chunks of Martian bedrock into space with enough velocity to escape the planet's gravity. These rocks can drift through the solar system for millions of years before crossing paths with our world. In 1984, scientists recovered a 4-billion-year-old Martian meteorite from the ice fields of Antarctica. When researchers examined a thin slice of this rock, ALH 84001, under an electron microscope, they discovered millions of microscopic, segmented tubes locked inside the mineral fractures. The structures looked so much like fossilized bacteria that the discovery was credible enough for the President of the United States to address the nation about the possibility of fossilized extraterrestrial life. If extremophile spores can survive for millions of years inside a frozen boulder, then the early seeding of Earth by Martian rocks is a viable scientific model. Under this theory, humanity's arrival on the red planet is a return to our planetary cradle. Sending a human crew to Mars is a biological nightmare. Outside Earth's magnetic field, interplanetary space is a shooting gallery of galactic cosmic rays. These heavy, highly charged ions tear straight through metallic holes in astronauts' bodies, breaking strands of DNA and triggering catastrophic cellular damage. If the crew survives the transit, they face an engineering trap during landing. The Martian atmosphere is too thick to allow for a simple rocket-breaking landing, like on the Moon, but it is far too thin to support parachutes for a 40-ton human habitat. On the surface, the soil itself is toxic. Breathing in fine Martian dust or eating crops grown in untreated regolith would introduce perchlorates into the bloodstream, blocking iodine uptake and triggering metabolic failure. To survive, a colony must live off the land through in-situ resource utilization. This diagram shows how the MOXIE instrument on the Perseverance rover acts as an artificial tree. It compresses the unbreathable atmosphere and rips the carbon dioxide molecules apart, stripping away oxygen atoms to generate pure, breathable oxygen gas. A permanent colony must industrialize the environment. By utilizing scaled-up oxygen factories, mining subsurface glaciers for water, and burying nuclear reactors to provide power through global dust storms, we can begin to sustain a human presence. While we establish our outposts, Mars is moving toward a massive astronomical shift. Its inner moon Phobos is locked in a fatal death spiral. Tidal gravitational forces are dragging the moon roughly 6 feet closer to the surface every century, a strain visible in the deep structural grooves etched across its face. In about 30 million years, Phobos will cross the Roche limit, where tidal forces overcome the moon's internal gravity. Phobos will violently shatter into trillions of basaltic boulders and dust, spreading out to encircle the equator and transforming Mars into a ringed planet. We are also contemplating the intentional transformation of the planet itself. Carl Sagan once proposed melting the polar ice caps to release carbon dioxide and warm the atmosphere. However, modern inventory measurements show that even if we melted every ounce of dry ice, the resulting pressure would only reach 7% of Earth's density. To thicken the atmosphere, we would need to synthesize hyper-potent artificial greenhouse gases. To protect this new air from the solar wind that killed the planet billions of years ago, we could deploy a superconducting magnetic dipole satellite to cast a protective artificial force field over the entire globe. Under this magnetic umbrella, the subsurface glaciers would melt and fill the ancient riverbeds once again. By introducing genetically engineered lichens and cyanobacteria to consume the toxic regolith and pump out organic matter, we could transform the iron oxide deserts into a living green oasis. Mars stands as a physical record of how a habitable world can lose its protection and bleed out into the void. It serves as a reminder that biospheres are fragile, while simultaneously offering the only accessible site to test the survival of our species beyond Earth. Our arrival on the red planet is the pivot point for becoming a multi-planetary civilization.